This is a second part of the chapter 22, second video. The alpha substitution reactions. Alpha hydrogens are acidic. We know that. We can replace them with a halogen or R groups. In order to do that, we have to convert aldehydes and ketones into enol or enolate ion. So we have two routes to do it. One, using acid as a catalyst, we can substitute the alpha hydrogen. Look at it, this one. This is an alpha carbon, and it has two hydrogen. I highlight one of them. If you treat this aldehyde with an acid, we know the aldehyde will become an enol. This is enol. If you treat the enol with a halogen, electrophilic addition, it comes there and pick up drop the proton. So you look at that acid is released here. We used it here. So it stays in the reaction. It will go ahead and act on another molecule. So it is a catalyst. In this reaction, the X also goes as X minus. What do you observe? First one, we substitute an alpha hydrogen with a halogen. This occurs through the enol. In this mechanism, the first step is the slow step. It decides the rate of the reaction. It involves the aldehyde and the acid. So the rate of this reaction is proportional to the concentration of the substrate. The substrate is the starting compound, aldehyde or a ketone, and the concentration of the acid. I wrote this one as proportional. If you want to convert this proportionality into equality, you have to use a proportionality constant K. Then the rate is equal to K times substrate concentration times the acid concentration. The K is practically is a proportionality constant, but we call it as a rate constant since we are using this rate equation. So what is the meaning of this equation? If you double the concentration of the acid, the rate of the reaction will double, occur twice fast. If you double the concentration of the substrate, the reaction will occur twice faster. Pretty simple. The net reaction, we replace a hydrogen with a halogen atom. I presented here. If you treat an aldehyde or a ketone with an acid and a halogen, one of the two hydrogen is replaced. The other hydrogen will be there. There are two hydrogens here. I have some examples. Aldehyde, you treat it with an acid and bromine, it replaces one of the alpha hydrogens, the bromine. So in this case, this is a ketone. You have two alpha carbons. This one has two hydrogen. This one has one hydrogen. This is more easy to replace it. So this will be the major product. The other product will not be formed. If it does, it will be a minor product. So if you have a ketone, you have to go to the carbon which has less hydrogens and replace the one hydrogen on it. Here I'm using the reagent D3O+. What is this D3O+? This is nothing but D plus D or D, just like water. This is heavy water. This is heavy hydrogen. This is heavy water reacts with it. This acts as a catalyst. This reacts like actually halogen we saw. So this will be replaced. One of the hydrogens will be substituted on the alpha carbon with a deuterium. The next, base promoted alpha substitution. Do you notice? Did you notice it? It is promoted, not catalyzed. Let us see the reason for it. This also occurs by the mechanism similar to that. This is an alpha carbon. You have two hydrogens. If you treat it with a strong base, it will come and pull it and put that here, and you form an enol cation. If you react it with a halogen, the same thing happens here. Goes away. Alpha carbon is substituted with one halogen. What happened to the base? Base becomes a conjugate acid. So the base is not a base anymore. This cannot be used again here in the first step. So it is not a catalyst. It is a reagent. It promotes the reaction to go faster, but it is not a catalyst. So that means you cannot use a catalytic amount of the base. You have to use one equivalent of the base. So in this reaction also, an alpha hydrogen is replaced by the halogen. This shows the mechanism. I put the same mechanism again. Why? Probably this is important. I think you have to learn it twice. You understand? No. Here is an alpha carbon. We treat it with a base. It becomes enol cation. Instead of reacting with a halogen, you reacted with an alkyl halide. Then this is going to happen. This will be an R group. Again, B goes as a BH, and the halogen goes as X minus. Same equation. So since the base becomes actually conjugate acid, it is not a catalyst, it is promoting the reaction. And then again, if you look at this mechanism or the previous one, it is a two-step reaction. The first step is a slow step. This is the rate determining step. So the rate of the reaction depends on the reagents involved in it, aldehyde and the base, their concentrations. I use the word substrate. You can have aldehyde or you can have some ketones. They are substrates, the starting one. The same way as we did it in the acid catalyzed, if I convert the proportionality into equality, I use the rate constant. It's a proportionality constant. So basically this rate equation, K times substrate concentration times base concentration. Same interpretation. If you triple the concentration of the base, the rate will be triple. The reaction will occur 3 times faster. If you triple the concentration of the substrate, the reaction will occur 3 times faster. The net reaction, again, we substitute a hydrogen with our group. But what is the base we can use it here? It should be a strong base. I actually, in the first video, I showed the bases. These are the strong bases, but they are not strong enough to abstract the proton. So we saw the use of NaH. This is not OH minus. NaH or NaNH2 or LDA as a base. But for these reactions, you can use OH, OR, NaH, and NH2 LDA. How can we use it? In the first video, we stopped there. We were talking about producing enolate ion. If you want to get a good concentration of enolate ion, you have to have a very strong base. If you use OH, the reaction will revert back, so that every time you will have a smaller concentration of it. But in this case, we take it to another step. There is one principle, you probably learned it in freshman chemistry, that is called the Lord-Chatelet principle. According to this principle, if there is an equilibrium reaction, yes, the first step is equilibrium. If you keep on removing the product of the reaction, more and more substrate will be converted into the product. If it is a case, if you use OH, there will be a small amount of the enolate ion, but that is not going to stay in the equilibrium, reacts with alkyl halide and goes here. So more and more aldehyde is converted into this. So we can use the OH and RO for this purpose. Before we go, keep this in mind, halogenation using base as a promoter is a Pauli substitution. What is it? Halogen replaces all alpha hydrogens in the molecule. But on the other side, the alkylation using base as a promoter is just a mono substitution. Only one hydrogen is replaced by the alkyl group. What is why there is a difference? Why halogenation Pauli substitution, alkylation as mono? Look at it, the product of substitution. After mono substitution, the next, this is also going to, if you put the base, it can abstract it and flip it, and then that can go. So it can be substituted again. But in the second one, if you look at it, this is an electron releasing group. This is also electron releasing group. No, this is electron withdrawing group. This electron releasing groups cancels part of the electron withdrawing group and make this as less acidic. So it is harder to remove it and put another alkyl group. But in this case, this is an electron withdrawing group. This is an electron withdrawing group. So both causes inductive effect. So this hydrogen becomes more acidic. Then it is easy to pull it and put another halogen. It is harder to remove it. The summary, X replaces all alpha hydrogens or replaces only one alpha hydrogens. Look at here examples. This is an alpha carbon. Alpha carbon. This alpha carbon has no hydrogen. You cannot replace it. The left side alpha carbon has only one hydrogen. If we treat it with a strong base and bromine, that will be replaced. There is no more alpha hydrogens to replace. In the second one, this is an alpha carbon which has two hydrogens. You're reacting with a strong base and halogen. All the alpha hydrogens will be replaced by the halogen. This is an alkylation reaction. This alpha carbon has two hydrogens, but you know the alkylation is monosubstitution. It will replace only one hydrogen with the alkyl group in the alkyl halide. The other hydrogen still will be there. This one, the same thing, we are using alkylation. There are two alpha carbons. If you use other bases like NaH or hydroxide or NH2, it will go to the more acidic alpha hydrogen and replace them. But since LDA is a bulky base, it goes to the less hindered alpha carbon and replaces one of them with alkyl group. When you write the alkyl group, be careful. This is an alpha carbon in the alkyl halide. You kick the halogen out, you connect the alpha carbon to that carbon. Okay. This reaction is possible in esters and nitriles too. This is a nitrile. These are alpha hydrogens. If you react with the sodium hydride and this one, it will replace one of them because it is alkylation. This is an ester. If you use the base and this, that is an alpha carbon which has two hydrogens. One of the hydrogen will be replaced by the alkyl group in it. Writing the product is pretty simple. The part 7 is acetoacetic ester and malonic ester synthesis. Listen carefully, because we lost some classes, organic faculties, all instructors who teach 228 assembled it together and talked about it and wanted to cut some parts of it. Everyone is in favor of cutting chapter 25 and 26. So they decided to cut those two chapters. But I decided to keep chapter 25 instead of that. I'm going to cut parts of less important parts in each chapter. So this one is a less important part. So we can skip this part. So I already cut some of them in aldehydes and ketones. Again, here, this part of it. In coming chapters, I get some less important part. So they will all equal to one chapter. So instead of cutting two trees, I cut one tree and cut some branches in other trees. I saved one tree. Part 9, alpha bromination of carboxylic acids. Say, for example, this is a carboxylic acid. We want to brominate it. So which one? Alpha hydrogen. So what are the two ways we learned? We can use an acid as a catalyst and then use the halogen in the step 2, the bromine. Or you can use actually a base in the first step, any base. The second step, use the halogen, bromine. These are the two methods we learned how to brominate or how to chlorinate. or how to alkylate alpha carbon. But in this case, this fails. This method also fails. We cannot alkylate it, alkylate the carboxylic acid, or we cannot brominate the carboxylic acid. But we have to do it. Why? Because if we have alpha bromo carboxylic acid, we can convert this easily into NH2 group. Then that is alpha amino acid. Alpha amino acid is the building block of proteins. So we have to get some amino acids. So we have to brominate it. Why we cannot brominate by that method? In the first method, if you use an acid, it should convert carboxylic acid into enol, then enol will react with it. If you use a base, it should convert the carboxylic acid into enolate, and the enolate will react with the bromine. But it is not possible for us to convert it into enol or enolate. Look at it here. You want to convert this into enol. You add an acid. You think this is going to pick up the proton, the bond will flip, and this will flip to form the enol. But this is not happening. Before that, this is happening because this is highly acidic. So you get the carboxylic acid again, the same one. So you were attempted to convert this into enol, failed. So we cannot brominate it. If you use actually a base to convert it into enolate ion, you want this OH goes here and abstract this and make it into enolate. Your hydroxide will not go there. Instead of it, it will go and pick up, abstract the proton from the highly acidic OH group. You get a carboxylate ion. It is not an enolate ion. So you cannot make it into enolate. That means you cannot brominate at the alpha carbon. So who is causing this trouble? The OH group. If the OH group is not there, if you have a hydrogen that is an aldehyde, if you have an alkyl group that is a ketone, they will undergo the enolization easily. So we have to do something to the OH group. Chemically, we call it protecting the OH group. We convert it into something else. Look at it. This reaction, you learned it in several chapters. So you treat it with BBr3. It converts the OH into BR. This is not carboxylic acid anymore. It is an acid halide. Now add an acid. The acid will protonate, so this will flip, and the alpha hydrogen may go down and then form the enol. This is enol now. Enol of the acid halide. You put the bromine there, the reaction is going to happen and flip it in. And you have this one. But this is not carboxylic acid. This is an acid bromide, alpha bromo acid bromide. So how to convert it into carboxylic acid? Just to react it with water. We learned that reaction in chapter 21. Acid halides react with water and form the OH. So this is the way we had to do it. The step one, we convert the OH into BR, so it cannot actually prevent the enolization. So we call this step protecting OH group. The last step We convert the BR into work edge. We bring back the original work edge. This is deprotecting the work edge. This is the way we can do it. So the net reaction, you take a carboxylic acid, treat it with tribromophosphorus, BBR3, and then water. So it goes to the alpha carbon and substitute the alpha hydrogen, one of them with the bromine. Same thing here. This is an alpha carbon which has one hydrogen. It is going to substitute that hydrogen. It is a mono substitution. Good luck. Keep healthy.